Hello students, welcome to EPG Pathshala and I am Rima Gupta from University of Delhi. So today we are going to discuss about the module Electrical and Magnetic Properties Part 10 and it is from the paper Ceramics. So students, let us see what we are going to learn in this module. So students, we will be talking about cubic and hexagonal ferrites and garnets. Then we will be discussing about the basis of magnetism and their applications. So before moving further, let us discuss what are ferrites. A ferrite is a type of ceramic compound composed of iron 3 oxide mostly combined chemically with one or two additional or more additional metallic elements. So they are both electrically non-conductive and ferrimagnetic, meaning they can be magnetized or attracted to a magnet. So ferrites can be divided into two families based on their magnetic coercivity, their resistance to being demagnetized. So the first is hard ferrites. Hard ferrites have high coercivity, hence they are difficult to demagnetize. They are used to make magnets for devices such as refrigerators, refrigerator magnets, loudspeakers, and small electric motors. Whereas soft ferrites have low coercivity, they have used in the electronics industry to make ferrite cores for inductors, transformers, and in various microwave components. So the ferrite compounds have extremely low cost, being made of iron oxide, that is rusted iron, and also have excellent corrosion resistance. So let us discuss about them one by one, and these are very stable and difficult to demagnetize and can be made with both high and low coercive forces. So, it was Yogoro Koto and Takeshi Teiki of the Tokyo Institute of Technology who has synthesized the first ferrite compound in 1930. So students, let us discuss about these ferrites one by one. So in terms of their magnetic properties, the different ferrites has often classified into soft and hard, which refers to their low or high magnetic coercivity. So first we are discussing about spinel ferrites. So these are cubic spinel ferrites. Cubic spinel ferrites have a chemical formula AB2O4 and they possess a face center cubic, that is FCC structure. In such crystal structure, two types of cations occupy the tetrahedral and the octahedral sites in a FCC lattice made by anions, that is O atoms. So one unit cell of spinel structured compounds consists of 8 formula units of AB2O4, which are determined by the distribution of cations in the interstices whose occupancy is only partial. Hence, one unit cell has a total of 32 octahedra interstices and 64 tetrahedra interstices. Because of stoichiometry, the octahedral interstices have 1/4 occupancy while tetrahedral interstices have 1/8 occupancy by the cations. So in summary, we can say that the partial filling of interstices is 1/4 filled for octahedra and 1/8 filled for tetrahedra. And the chemical formula is AB2O4. So some of the example for normal spinels are zinc ferrite, that is ZnFe2O4, magnesium aluminate, that is MgAl2O4, cobalt aluminate, that is CoAl2O4. So here A is tetrahedral and B is octahedral. However, the examples of inverse spinel is iron oxide and nickel ferrite. So depending on the distribution of cations in octahedral and tetrahedral interstices, cubic spinel structures can be classified as normal spinels and inverse spinels. So the magnetic moments of cations occupying tetrahedral sites are opposite with respect to the cation occupying the octahedral sites, and hence these are essentially ferrimagnetic materials with a Curie transition and soft magnet-like behavior. So the example of normal spinel are zinc ferrite, that is ZnFe2O4, which we have already discussed, and in these compounds all the A atoms occupy tetrahedral, that is 1/8 of occupancy, while all B atom occupy octahedral, that is 1/4 occupancy. On the other hand, many of the iron containing spinels are inverse spinels, such as iron oxide, nickel iron oxide, that is NiFe2O4, and some others are cobalt ferrite and so on. In these, 50% of B cations occupy the tetrahedral sites and all A and remaining 50% B cations occupy the octahedral sites. Hence, one can write the formula as A tetrahedral, AB octahedral, O4. For example, the spin arrangement of Fe3O4 is shown in the next slide. So students, you can see the spinel structure which is shown in this slide. So on the left hand side, you can see the arrangement of oxygens and A and B cations in octahedral sites and tetrahedral sites. Whereas on the right hand side, you can see the octahedral interstices which has 32 per unit cell. Whereas on the lower right corner, you can see the tetrahedral interstices which has 64 per unit cell. On the left hand side of the figure, you can see the crystal structure of spinal structure compound, that is MgAl2O4. So as we have discussed, this crystal structure has normal spinal structure. So in case of normal spinal structure, all the A atoms occupy the tetrahedral sites, that is 1/8 of the occupancy, while the B atoms occupy the octahedral interstices, that is 1/4 of the occupancy. So students, you can see on the lower right corner a figure showing a magnetic moment of Fe3O4, that is an inverse spinel compound. In this case, the net magnetization of Fe3O4 is 4 of mu B per formula unit. Similarly, one can estimate the magnetic moment of other inverse spinel ferrites like nickel ferrite, that is NiFe2O4, cobalt ferrite, that is CoFe2O4, as well as of mixed spinels. One can tune the magnetic moment and Curie's temperature of spinels by preparing the solution of two spinel compounds at most are miscible into each other, such as the mixture of zinc ferrite and nickel ferrite can be formed. In general, cubic spinel ferrite possess low magnetic anisotropy and are soft magnets. So as we have discussed in the previous slide, the magnetic behavior. So the magnetic behavior for the spinal structures are, they have low magnetic anisotropy and are soft magnets with low coercive fields. So there are few exceptions such as cobalt containing ferrites, which not only possess strong anisotropy but also exist large magnetic coercivity. Hexagonal ferrites. The hexagonal ferrites are based on hexagonal magnetoplumides and are often called M-type ferrites. The model compound of this family is barium ferrite with formula BaFe12O19. The large hexagonal unit cell contains 64 atoms, that is 2 formula units. The structure is basically a mixture of cubic closed packed and hexagonal closed packed layers formed by barium and oxygen ions. The chemical substitution of barium sites is usually done with strontium atoms, while iron atoms are substituted by aluminium atoms. So it is based on size and valency, resulting in change in the magnetic behavior. So in hexagonal ferrites, out of 12 iron atoms of one formula unit, 9 occupy the octahedral sites, 2 occupy tetrahedral sites, and remaining one is 5-fold coordinated. So out of these, 7 atoms on octahedral sites and one with 5-fold coordination have their spins in one direction, while spins of rest of the atoms are oriented oppositely, that is, say, 8 atoms with spin up and 4 atoms with spin down. So as we saw earlier, each Fe3 plus ion has spin magnetic moment of 5 mu b, and simple, it gives a net magnetic moment of 20 mu b per formula unit, leading to magnetic moment of 40 mu b per unit cell. So let us discuss the magnetic behavior. So the hexagonal ferrites have high degree of magnetic anisotropy and it magnetizes relatively easy along 0001 direction or c-axis of its unit cell. The material is typically categorized as a hard ferrite with coercivity between 50 to 100 kiloamperes per meter depending on the microstructure and the composition. Now come garnets. So students, you can see the crystal structure of garnet structured compound on the left hand side and the mineral corresponding to it on the right hand side. So let us discuss its properties and structures in the following slides. Garnets are usually known as minerals. In the context of magnetic material, the garnets are based on Y3Fe5O12 represented by a general formula R3Fe5O12 containing 2 magnetic ions, one typically being iron and another being rare earth. Here, R in addition to yttrium can be one of the lanthanide atom such as lanthanum, cerium, samarium, etc. So the unit cell of Y3Fe5O12 is cubic and contains 8 formula units. So in continuation to previous slide, we have discussed that the unit cell of Y3Fe5O12 is cubic and contains 8 formula units, that is 160 atoms, which is quite complex. So in general, the garnet ferrites, the orbital magnetic contribution of iron atom is quenched due to shielding from crystal fields, while lanthanide ions contribute to both orbital and spin magnetic moment, thus contributing more to the total magnetic moment. Let us discuss the magnetic structure of garnet. So in this structure, our atoms have a cubic coordination, that is 12-fold coordination. Two iron atoms, that is 2 Fe atoms, have octahedral coordination, while remaining 3 iron Fe atoms have tetrahedral coordination with anti-parallel spin configuration of spins on tetrahedral and octahedral sides, while the orientation of spins on our side is parallel to those on octahedral sides. We now know that each Fe3 plus ion contributes to 5 mu B, which each lanthanide atom, that is R, contributes a moment of magnitude mu B into mu R, where mu R is the strength of moment of our ions. Hence, the total picture looks like following, which is shown that 3 R atoms having 12-fold coordination whose spin is down, 3 iron atoms having tetrahedral coordination, spin is up, 2 iron atoms with octahedral coordination. So overall it is 5 minus 3 mu B into mu B. So the value of mu R is 7 for GD while 0 for Y. Hence, the magnetic moment would be dominated by rare earth. Dominated by rare earth ions when mu R is greater than 5/3. Temperature dependence of magnetic moment. So, it is dependent upon the temperature which governs the coupling between rare earth and Fe ions, that is iron ions. Typically, the net magnetic moment drops as the temperature increases, especially for strongly magnetic ions like godium, Tb and Dy. So the GD doped garnet of composition, that is Y1.2, GD 1.8, Fe5O12 has rather stable saturation magnetization for a wide temperature range centered around 50 degrees Celsius. So, garnets can be quite useful materials in microwave applications because of their high electrical resistivity and hence lower loss and around microwave frequencies. The material is also easy to synthesize in either of bulk and polycrystalline ceramic. It is a single crystal or thin film form it is available, and moreover the structural parameters as well as the magnetic properties can be tuned by tailoring the composition of the material. Properties of soft ferrites. So as discussed previously, ferrites have a broad spectrum of properties depending upon the type of ferrite and composition. So soft ferrites are materials which are easy to magnetize or demagnetize. So higher resistivities than typical ferromagnetic metals, leading to low eddy currents in the core. The low losses at higher frequencies make them useful for high frequency applications such as cores of RF transformers and inductors in SMPS. So nickel zinc ferrites show higher resistivity than magnesium zinc ferrites and hence are more stable for frequencies above 1 MHz. The magnesium zinc ferrites on the other hand have higher magnetic permeability and saturation magnetization. Tailoring improving the properties of soft materials. So it can be tailored by compositional modifications. So for instance, in Mn zinc ferrite and nickel zinc ferrite, increasing the content of zinc leads to an increase in the magnetic permeability, and magnetic transition temperature decreases due to reduced magnetic anisotropy. The change in grain size also has a profound effect on the relative permeability, with permeability increasing with increasing grain size. In ferrites, D group elements are susceptible to valence fluctuations, and for example, Mn zinc ferrite are more susceptible to valence fluctuations in Mn and iron as compared to nickel and zinc ferrites. So for example, in nickel zinc ferrite, if all of the iron is present in 3 plus valence state, then alpha is 0. Any increase in the iron content, that is alpha greater than 0, is compensated by the formation of Fe2+, which creates favorable conditions for electron hopping between Fe3+ and Fe2+, promoting n-type conduction. On the other hand, the deficiency of iron, that is alpha less than 0, is usually compensated by oxygen vacancies, resulting in large increase in the resistivity, about 8 orders of magnitude. So such behavior is shown in the figure on the left hand side, where x-axis shows the Fe content, that is alpha, and y-axis shows the log resistivity in ohms meter. So this resistivity variation in nickel zinc ferrite is as a function of iron content. Now comes the properties of hard ferrites. As we know, the remnants in materials like hexaferrites, which are strongly anisotropic, can be affected by processing. Since the effect of magnetic anisotropy in a polycrystalline ceramic is small, so the material can be synthesized under application of a magnetic field, thereby aligning moments along C-axis in the grains, giving larger remnants, and hence the coercivity is a strong function of grain size, and it is found for hexaferrites that it is maximum for grain size of about 1 micrometer. So let us talk about the applications of magnetic ceramics. So they have wide range of application in electronic inductors, transformers, and electromagnets. So we have discussed that earlier in intro also, that soft ferrites like manganese zinc, that is MnZn, and nickel zinc, that is nickel Zn ferrites, are used as core materials in these applications like inductors and transformers in the frequencies ranging from 100 kilohertz to 100 megahertz, and typically these ferrites have high electrical resistance, which results in very low eddy current losses. So most common ratio magnets, example in loudspeakers, are made of ferrites. In fact, in many of these applications, ferrite magnets have largely substituted traditional Alnico magnets. So ferrites are also used for power transformers, which are used to transmit either over a single frequency or within a range, such as ultrasonic generators. So for high frequency applications up to about 5 megahertz, nickel zinc ferrites are useful, while for frequencies up to 100 kilohertz, manganese zinc ferrite are preferred due to their high permeability. So the equipment shielding is the another application. So here Due to their high impedance of high frequency currents, ferrite components of nickel zinc and manganese zinc ferrites are capable to protect the equipment from high frequency electrical noise due to electromagnetic interference. So, they can be used in data storage, in the magnetic tapes, elongated. So, the magnetic tapes are the elongated ones of zero point 0.2 to 5 micrometer long hard magnetic oxide particles of gamma ferrite, that is gamma Fe2O3, and they are embedded in non-magnetic binder. So the particles have single domain magnetized along with their major axes, which are aligned in the planes of the tape. The coercive fields are typically between 50 to 100 kiloamperes per meter. So in magnetic hard disk, core elements is produced by forming several layers of materials, that is non-magnetic underlayer or magnetic layer, and these are overcoated and plus layers of lubricants. So here the read-write head is not in direct contact with the hard disk as compared to the floppy disk due to air bearers, in which the airflow is caused by the relative velocity between the disk and head. So these memories have high storage density of about 10 gigab, or we can say GB per inch square, and short access time. So early generation computers and memories and hard ferrites cores which were used to store the data, and ferrite powders such as Fe2O3 is used as coatings on magnetic recording tapes, for example, in absorbing materials. So, in strength aircrafts, ferrite particles are used in as radiation absorbing materials for low frequency applications. Moreover, the magnetic materials have their wide range of applications in microwave also in the frequency 1 to 300 GHz. Materials like magnesium ferrites, lithium doped ferrites, and garnets are used for such applications such as phase shifters, circulators, and isolators, and so on. So students, now let us summarize what we have learned in this module. So while most ferromagnetic materials happen to be metals or alloys, many spinel structures, oxides, ceramics, especially those containing iron and other magnetic elements, example Fe2O4, Fe3O4, tend to be ferrimagnetic. However, there are other oxide ceramics such as hexagonal ferrites and garnet structures, oxides, which show only reasonable large magnetic moments. So these ferrites are useful for variety of applications which we have discussed in details, like electromagnets, shields, data storage, and microwave applications, etc. Thank you.